All right. Welcome back. How was lunch? Okay. Glad to hear. Okay, we're going to get started with our afternoon keynote. I'd like to welcome to the stage Dr. Natalie Hinkel. Dr. Hinkel studies the composition and the abundance of materials in stars, and she built the Hypatia Catalog, which is the largest catalog of such information. Dr. Hinkel. Thanks so much.
Hi, everybody. Thank you so much for having me here. I'm actually really excited. I live in San Antonio, so it's not too far away. But I'm really excited because I know that having astronomers here is not the most common thing. So, in fact, clap if you're a physical scientist here. So there's 10 of us. Awesome. Great. But anyway, I forgot my clicker. So what I'll be talking with you today about is elements in stars. So I'll first go over some of the physics behind that, and I'll discuss the Hypatia Catalog, which is like sort of the crown jewel of my research. Then I'll talk with you about signatures of exoplanets in stellar compositions. Then I'll go on to talk about some machine learning and what I've done to look at stars and, that have exoplanets. So these are planets that we've discovered outside of our solar system. And then I'll sort of wrap that up by talking about how we can go from the stellar composition to the planets using different kinds of models. And then I'll wrap it up by talking about interdisciplinary fields. All right, so I usually like to start my talk at the beginning, and in this case, this means the Big Bang. So when the Big Bang happened, the first elements that were created were hydrogen and helium. That was it. There was no carbon, there was no oxygen, no iron, none of these things that we sort of take for granted nowadays. So this hydrogen and helium, it shot out all over the universe, but the universe is not flat. In fact, it's made up of sort of these different densities. So what happens is that you get these big balls of hydrogen and helium, and they end up collapsing in on themselves, and they create stars. So it's within these first stars, which are huge, they're like 1,000 times more massive than the sun, that we have fusion. They have temperature and densities that are high enough that we have fusion. So you finally, for the first time, you take hydrogen and hydrogen, you slam it together, you get helium, you keep doing that, and you get carbon. And you keep doing it a little bit more, you get oxygen. So within these first stars, we get the seeds of new elements. But these big stars, they live fast and they die young. So they explode. They explode and they shoot these new elements all over the universe. So the next stars that are formed, they're mostly made up of hydrogen and helium, but there's also these little carbon seeds and oxygen. And so they start building off of that. And then they explode, and they shoot that everywhere. So eventually, it's because of stars that the majority of the periodic table is created. So this is an image that was created by a colleague of mine, Jennifer Johnson, at Ohio State. And what this is a color-coded version of the periodic table to show you where these elements come from. So you see the blue is what is from the Big Bang, like I said. And then you have the green and the other blue, the slightly lighter shade of blue, that is coming from massive stars. So this is mostly from like supernovae, the actual explosions. And then the yellow and the orange are from different kinds of stars, merging neutron stars, or even sort of the end products of low-mass stars who kind of slough off the elements that are at the top of their atmospheres. So this is really important, and it's really interesting, and it's for that reason that I created the Hypatia Catalog. So this is a catalog of element abundances that we have measured within stars. Hypatia is a catalog that I put together by combining multiple different data sets, 171 different data sets. So by definition, by the superposition principle actually, my catalog is the biggest. Size matters. So a total number of stars that I have is 6,156 stars, 72 elements. This is 2 or 3 times bigger than any other data set ever, regardless of the distance. All of these stars are F, G, or K type. That means that they are relatively similar to the sun. The sun is a G2 type of star. But then we have a few M dwarfs. And I say that because you might start hearing more and more about M dwarfs. They're becoming the new hotness in astronomy. And all these stars are near to us. They're all within 150 parsecs or 500 light years. And the reason for that distance cutoff is because this is what we really need to get high resolution data to get all these different elements. So what you're seeing on this above me, and the point of it is not so you can read it. I know that these letters are tiny, but it's all of the elements that are in Hypatia and the number of stars for which they've been measured. So it's a huge number, but you can also see sort of the state of the field. What elements are we able to measure very easily? For example, iron is the one that's at the very top. But then there are a lot of elements, for example, these heavier elements at the end that are obviously going to be a little bit more difficult. Now, I always get this question, so I like to address it head on. Who is Hypatia? Hypatia is one of the first known female astronomers. She lived around 400 AD, and she was really well respected in her community. She taught not just astronomy, but math and philosophy, and she taught from her own house. And she was so well respected that magistrates would often come and ask for her opinion. But because of her influence, especially in the political realm of the community, that sort of put her between two different groups, and as a result, she was unfortunately killed. But the more I read about Hypatia, the more I realized that she's a badass. So I wanted to honor her by naming my database after her. Now, the database itself lives on my laptop. It's backed up in a bajillion ways, but I wrote the back end of it in Python. It's one of the only multi-dimensional data sets in astronomy. And I know that sounds kind of weird when you're not sort of in the direct physical sciences, but typically what happens in astronomy is that you have a mission or a satellite, and it measures properties for stars. Well, I have properties for stars written as measured by different groups, and some of those stars have planets. So this was a little bit complicated when I started putting it together. So like I said, it's made up of 171 different data sets, half of which were machine readable. The other half I actually had to convert by hand. So I did the public service. But all these data sets are different. In fact, the way that I think about them is that they're their own unique beasts. They have different elements, different stars, different ways that they measured these the elements within their data sets. So the way that I incorporate them is I set up a class of class structures such that each star is a class where I tack on the physical properties, because these properties are super important for astronomers. We need to know the distance, the magnitude, how bright is the star, how fast is it moving. Then I add on all the elements that were measured by these different data sets, making sure I keep reference to that. So in this way, the data set is flexible. I can continually add to it, which I do, and I can modify it in any way such that the data is malleable, and I can flatten it to 2 dimensions whenever I need to plot or make talks and things like that. So the core functionality, though, of Hypatia is actually not just to put all this data together, but it's to renormalize these data sets. There's a standardized scaling method that people use. However, it's not actually that standard when you go look at it. We try to normalize everything to the sun. But the sun has a variety of different measurements. So what I do is I take off that scaling to the sun, and I put on the same scaling for everybody. So in this way, when people use the data, they're actually comparing apples to apples as opposed to apples to oranges. Now, I've been working on Hypatia for about 9 years, and it was only within the last 1.5 years that I started working with this wonderful web developer to help me put it online. So now all the data can be accessed at HypatiaCatalog.com. In fact, you'll notice that it uses bokeh. So thank you, Anaconda. So this is a way to plot a bunch of the data that we have. So what you're seeing here is sodium with respect to iron, and the colors are the distances. So you can see some of the information about these stars. For example, the darker stars, the one that sort of have that concave effect, that's indicating that these elements from these stars came from different nucleosynthetic origins. So this has real meaning to it. But there's a lot of stuff that you can do with this data, and like any astronomer loves to do, I wanted to make sure that they could plot everything versus everything. This is actually a joke within astronomy. So we have this wonderful drop-down periodic table, which also lets you see the stellar properties and the planetary properties, if some of them exist. Now, I mentioned that the database is multidimensional, and it is, but I wanted people to access that data without being completely overwhelmed by it, because in total, I have 280,000 different abundance measurements. So I allowed people to look at this data in 2 dimensions if they wanted it, but if they wanted to see where this data came from, they can actually click on any of these values and see how many different groups measure this element for this star, and then at the top, they're able to change it or remove it, look at particular data that they want to. So this is the technical side of it, but the truth of the matter is that we want to look at these element abundances because ultimately we want to understand the different chemical history of our galaxy. So this is a mock-up of the Milky Way. This is not actually a picture. We don't have a picture. And so we have all these different chemical compositions that we can measure. So what you're seeing pop up right now are different elements that we can measure. This is coming from the Apogee and the Galah survey. That's what you see fanning out. So it's from this data that we can look at the different kinds of stars, stars that are in the spiral arms of the galaxies, stars that are in the thin disk versus the thick disk. Then as we zoom in, we can start looking at more properties as we start understanding the physical properties of the star. How fast are they rotating? Are they moving through the disk or not? Do they have different kinds of elements that we should be aware of for the different kinds of supernovae that went off? So what we're zooming in on now is the data from the Hypatia Catalog. And so what this lets us see as we get closer and closer is how many stars that actually have abundance measurements versus all of the stars that we've actually had that we can actually measure. So, for example, the Gaia satellite the Gaia survey has been looking at nearby stars. They've measured 9 billion stars. This is 3 million. I already had a hard time rendering it. So we have a lot of information about these stars. We have physical properties, and we also have the chemical properties for some of them. But now, in the last 25 years, the exoplanet field has started to emerge. So now we're also interested in looking at stars that have planets. So that's what you're looking at now. So the stars that are in blue are actually indicating stars that have planets that were observed from the ground. But those that are in yellow come from the Kepler satellite. So we're getting tons of new information about stars with planets, and then we're able to compare those to stars without planets. So like I said, the exoplanet field is relatively young. In fact, I realized only recently that it's barely old enough to drink if it was a person. It's 25 years old. So the first exoplanet was discovered in 1992, but it was discovered around this crazy kind of star. It's called a pulsar, which has a huge beam of light and radiation, which is not super fun if you live on that planet. So in 1995, it was the first planet around a solar-like star that was discovered. And since that time, the entire field has just shot through the roof. So you can see on this plot, these are all the detections that we've had over the last few years. And so the ones that are in green are coming from the Kepler satellite, which is drastically increased all the number of stars with planets that we've been able to detect, which is super exciting. But like I said, I look at stars and I look at the elements of stars. So the sort of obvious question is, can we see a signature of planets within the stars, within the composition of the stars? And the answer is kind of. So it's sort of a known fact at this point, from my perspective, this is going to be new information for you, that stars that host giant planets, Jupiter-sized planets, like big planets, are preferentially enriched in iron. This makes sense. You need a lot of stuff in order to make other big stuff, so you should have more iron. Okay, that's great. So multiple data sets, everybody agrees on this. This is so true that if you don't get this, then you're definitely doing something wrong. But then the next question is this true for other kinds of elements? And so people started looking at other elements. They started looking at sodium and magnesium and manganese, things like that. But people couldn't agree. Even if they looked at the same elements, they couldn't agree. Some people would say that stars were enriched in some elements, and other people would totally disagree. There was actually kind of a war in the literature about this. We've even had talks, conferences, trying to figure this out. But nobody can agree. So then I was like, well, what if we use machine learning to try to understand some of these more subtle trends that we clearly are not being able to see? We're using simple statistics. We're comparing one element at a time. So let's try some machine learning algorithms to help us out. However, because we're dealing with actual data and actual observations that come from satellites, we do have to be careful about biases in our data, because they are definitely there. And while some people I know argue that we should wait until everything's perfect and not biased, we aren't ever going to be there. So I figure as long as we sort of recognize what we're working with, we'll be able to make some real progress. And like I said, the other thing I wanted to address is, what if we don't just look at one element at a time? What if we look at multiple elements? See, the way that I think about elements in a star is sort of like minerals and vitamins in your body. Sure, you can take that B vitamin if you're not feeling very well, but it's actually better for you if you eat the fruits and vegetables that you're supposed to, because these minerals and these vitamins, they work together in your body to give you what you need. So in a lot of ways, I think that actually these different elements within planets are similar. So what I did is I created different ensembles of elements that were sort of linked together in two ways. Either they came from the same nucleosynthetic origin, i.e. the way they were created in stars, or they are related to each other geologically. So we have the volatile elements, which burn up relatively quickly. They have a low condensation temperature, so that's fairly simple. You have lithophile elements. So these are elements that sort of exist near the surface of a planet, and they're oxygen-loving, so they tend to bond with oxygen. So that's what lithophile means. And then you have siderophile, which are iron-loving elements, which tend to sink to the core and then bond with iron. Now you may notice that when I created the different ensembles which I've listed, I've kept iron out. Iron is obviously going to be a siderophile. It loves itself. But iron is the one thing that we see in the observations that we know is enriched in stars with planets. So I wanted to make sure that we saw this within our own machine learning algorithm results. But on top of that, I wanted to see if iron influenced the elements in any particular way. So that's why I sort of kept it separate. All right, so the algorithm that I wrote is kind of like Netflix. So I used XGBoost, which is a supervised classifier per gradient boosted trees. And so you watch Netflix, right? And you watch a bunch of movies, and it learns the trends of movies that you like. So I really like goofy 90s comedies. So it takes that idea, the trends that I like, and it applies that to its back catalog of movies I haven't watched, and then it recommends that I watch these movies that are similar to goofy 90s comedies. And then it emails me that I should watch them, and then reminds me that I should watch them, and pops it up when I don't want it to start playing the movie all the time. So it just does it over and over again. So the algorithm that I wrote is very similar, is that I trained the algorithm to look at the elements of stars that have planets. So these are confirmed planet-hosting stars. And I train it to learn the trends within those elements. And then apply those trends to stars that do not currently have confirmed planets, and predict whether or not these stars are likely to have planets. And then I do that thousands of times. More pictorially, it kind of looks like this. And I sort of mention it because there is a difference between the different sample sizes that we have. The stars within Hypatia that we know have planets is total 320. But the stars without planets is 4,800. So wanted to make sure we were comparing everything correctly. So what I ended up doing is essentially taking a scoop of each of the samples, comparing those, training the algorithm, and then applying it to the subsample of the stars not currently known to host planets. And then I do that thousands of times. And this way, we ensure that every star within Hypatia that doesn't currently have a known planet is sort of touched on a bunch of times so we have a statistically significant sample. So the end product of this is that we get some important features. So these are the elements that help break down our population of stars to say, you are likely to host a planet, and you're not. The way I sort of like to think about it is like taking a big group, so even like people here today, and everybody here, we have a high entropy. We are different heights, we're different ages, we come from different places, we work on different things. But once you start segregating people off using those properties, then that will help you lower the entropy of your system. So in this case, it ended up being that carbon, oxygen, and iron were the most important elements that distinguished whether or not a star is likely to host a giant planet. Now, the order of this, I list one of the plots here that gives the order, but the order actually varied between those three. So those are definitely the most important. But interestingly, when those three elements weren't there, sodium was the next most important thing. So carbon and oxygen, I understand that. We're talking about giant planets, so those are mostly gaseous. We're talking about gases. This makes sense. Iron, we reobserved from the data, so that's good. But sodium's weird. Sodium comes from low-mass stars, from high-mass stars. It comes from all over. It is kind of important for rocks and for planets, but not super important. So actually, this sort of left us at a little bit of a loss because we're not really sure why sodium's important, and yet it kept coming up. So this is sort of interesting for us to look at. So in addition to these 4 different elements that are important, we wanted to make sure that what we were looking at made sense. So right now, we don't have any true negatives. There are no stars that I can tell you that do not have a planet. We don't know that. Our detection methods are limited. We are biased towards giant planets. We can't even observe a system like our own solar system. We just can't right now. So without a true negative, what I decided to do was use a golden set. We took a number of stars that we know have planets. We took that out of our training set, and we hid it within our predictive set. And then we applied our algorithm to it to see how it would come out. And we found that over 75% of the time, these stars that we know host planets were likely to have planets. So good, that was great. More than a coin toss. But what was really interesting, and it's sort of hidden in this simple statistic, is that in the vast majority of the cases, these stars that are confirmed planet hosts were given a greater than 90% chance of hosting a planet. But then there were a bunch that had 0% chance of hosting a planet. So to continue on my metaphor kick, it's like Rotten Tomatoes. So if a Rotten Tomatoes has a movie score that's over 90%, you're like, well, this is definitely going to be a good movie. But just because it has a low score, it doesn't mean it's a bad movie. It doesn't mean it's not likely to host a planet. So, I mean, I like bad movies too. The other thing that we produce from this algorithm is a list of stars with a greater than 90% chance that they host a planet, which is super exciting because I'm actually going to start applying for a telescope time to try to confirm these planets. And this is a great framework for the community because right now we have these big sky surveys, but what if we can start pinpointing different places where we can really expect that has a high chances of predicting a planet? So I'm really excited about that. So right now I've been talking about how planets may influence a star, but there's also ways in which a star can influence a planet, as was put very well by the Magic School Bus, from which this is a picture. Like I said, you take a big ball of gas, you smash it together, and then you form a star. But this process isn't perfect. So you get extra dust and gas that's left over. Then this dust starts slamming together, and you get pebbles. Pebbles become boulders. And from boulders, you get planets, which ultimately means that stars and planets are formed at the same time and from the same material, which is really, really exciting. But we need to know a lot of information about planets, because ultimately, in the exoplanet field, the whole reason why this field exists is because we want to find a planet that may have life already or could host life like us. That is the whole driver behind the exoplanet field. We want to find something that's kind of like the Earth. So the first thing that we really look at are the physical properties. So this is called the habitable zone. So these are the different colors that you're seeing. If a planet's too close, then it's too hot. If a planet's too far away, it's too cold. This is also called Goldilocks zone. I hate that. So we want to know where these stars or planets are with respect to the stars. We want to know what their orbits are like. Earth's orbit is almost a perfect circle, so eccentricity is 0. But there are some planets that have an eccentricity of 0.92. The max is 1. That means it spends the vast majority of its time flying away from or towards the star. It's super cold. And then for a very tiny amount of time, it's incredibly hot. This is not great for life. So knowing these sort of properties are important. We also need to know the planet's mass. Is it Earth size? Is it Jupiter size? What if it's kind of in between? That's actually a question we're still asking, because right now we don't have any sort of analogs within our own solar system that's at like a 2 or 4 Earth mass. So what would that be like? But in addition to these physical properties, we need to know the chemical properties of the planet. So this is a pie chart that shows all the different elements that are on the surface of Earth. So there's a lot going on here. But then you also need to know what's interior to the planet. You need to know its interior structure and its composition. Because when you're looking for a planet that's habitable, that planet also needs to be alive. You need to have different cycles, geochemical cycles, that move some parts of the elements to different parts of the Earth. You need it to go up into the atmosphere, fall back down, and cycle back through. This is how you get new materials to different parts of the planet, and you get life to begin. So having these different properties, these different chemical properties of the planet understood is a very big part of understanding its habitability. In fact, we're just starting to look at this. I'm one of 5 people in the world who actually studies the chemical properties of a planet. So some colleagues of mine and I looked at the TRAPPIST-1 system. This came out about 2 years ago. And it's cool because the system is crazy. There are 7 planets around a really tiny, cool star. It's an M8 star. And you can see from this image that all of the planets are all smashed in such that it's actually easier to compare their scale with the scale of Jupiter and its moons than it is to compare it to our own solar system, which is what you're seeing at the bottom. So everything is like really smashed in together. But these 3 planets that you're seeing that are demarcated with the red lines, they are in what's called the habitable zone. But my collaborators and I, we looked at these planets and we're like, these planets are a little weird. Given their mass and their volume, it seems like they're kind of puffy. So we took the composition of the host star, we put it into a model that actually creates the interior structure of a planet. And what we got were these figures. Now, what we're looking at is the depth of the planet. So the 0 is the surface, and at the bottom is the core. But the biggest thing you want to take away from this is that it just says ice everywhere. These are water worlds. These are planets that were said to be in the habitable zone. People kept saying they're habitable, but the vast majority of them are water. And despite the fact that we, as humans, need water, too much water is bad. It actually limits the habitability and the different life biomes because you're not able to get the cycling of the different elements from the lower parts of the planet to the higher parts. So it's likely that these are not actually habitable planets. In fact, when I was working on this paper, it kind of set off a thing that I started to notice, is that there's kind of a disconnect between a variety of the different fields. There's a bunch of elements that we measure in stars, and this is sort of a chunk of the histogram I showed you earlier. And there's some elements that are really easy to measure within stars. We look in the optical band of the electromagnetic spectrum. A lot of these elements have a bunch of lines within that band. And those are the ones we focus on, because we can get them, because they're easy. But when I talked to geologists, they started telling me about what are the rocks that are the elements that are most important to rocks to building planets. So that's what's listed as the major and minor rocks. Then when I started talking to astrobiologists and oceanographers, well, what are the elements that are important to you? They started giving me totally different elements. So this is what you're seeing for major, intermediate, and minor life. Well, the more I looked at it, the more I realized, well, crap, guys, we kind of have a problem. Because some of the elements that are important for forming planets, that are important for life, are not really well measured in stars. So this is actually a problem that I started working on with a collaborator, Hillary Hartnett. She's at Arizona State. She's an oceanographer, and so what we started doing is I tried to collect as many phosphorus abundance measurements in stars as I could. We have 92 stars that have phosphorus measured in it, 92. So we're like, okay, what can we do with this? So this is the plot that you're seeing. The green are just stars. The black are stars with planets. The yellow circle at the top is the sun. And what you're seeing at the very bottom down here, yeah, that's the Earth. That's plankton, the Earth's crust. We can't tell very much from this. We know that the sun looks totally nuts compared to other stars and compared to other stars with planets. We know that stars with planets are enriched in phosphorus. Cool. We know that the Earth is nitrogen poor and phosphorus rich compared to the sun, yet we also know that we need both nitrogen and phosphorus for life. In fact, when we sort of came down to it, we realized that life, so this is this little green clover thing, more closely resembled the star than it did the planet. But this is only 92 stars. This is not actually enough to build a whole science case off this. This is not statistically significant. So there's a big gap right now, something that I've really been working on. I call these elements interdisciplinary elements. These are elements that have sort of been skipped over by astronomers, by spectroscopists, but we need them in order to actually start to connect stars to planets to life. So overall, there's a lot to do in the future, which I'm excited about because that means that I have job security. So I've been really focused on expanding this definition of habitability. A lot of people within my own field, they really just focus on whether this planet is at a good distance from the star. But what I keep yelling back at them is that you can't just say this is a good place to have liquid water. You also have to say, is there liquid water? And what about all the other elements that are really crucial to us, to life? I've been working on trying to make some interdisciplinary collaborations and not just talk to people at conferences, but actually make connections, to email them, to start writing papers with them, to learn what they mean when they say certain words. I learned what fugacity means. Because people just say these things. You say jargon, and nobody from another field would even understand it. So there's not only the word barrier, but it's trying to understand what do people need, what do they want in their data from their models, where do they want to go, not just the next step, but 10 steps from now that we have to sort of prep to get to it. And the other thing is, and this is something that I think most people here would be really interested in, is that there are huge satellites and missions that are tooling up, will be tooled up soon, that are going to produce so much data. And I will say this meaningfully and truthfully. We as astronomers don't know how to handle all the data. We don't. We're trying. Like any good scientist, you try to teach yourself. But when I started coming to people about the fact that Hypatia was a multidimensional data set, astronomers have no idea what I was talking about. I started talking to computer scientists, and they were like, this is not a big deal. So it's important for us to start talking to one another because there are problems that can be handled better by you than by me. But there are physical properties, chemical properties of these different stars, of the things that we're looking at that you wouldn't understand, but I do. So it's not just that one thing needs to be handed off to a different person and just said have at it. It actually means true collaborations. But that's something that I'm really excited about because it means that I have the chance to grow, to learn from other people, and start applying that to a variety of different aspects for my field. So in conclusion, stars and planets and life are all connected. But the exact ways that that's true, how it actually comes about, we're still figuring it out. But that's okay because this field is the youngest field that exists. Thank you.